This video is about specific heat capacity and specific latent heat. We'll begin by looking at the basics of specific heat capacity and specific latent heat, and finish up with a more complex example involving these two concepts. Let's begin with specific heat capacity. Specific heat capacity is defined as the energy required to raise the temperature of 1 kilogram of a material by 1 Kelvin. Since the change of 1 Kelvin is equal to a change of 1 Celsius, we could replace Kelvin here by degrees Celsius. Here is the formula that includes specific heat capacity, and here are the variables in this formula. When we rearrange this equation for C, we get Q over m times delta T. From this it follows that the unit of specific heat capacity is joules per kilogram per Kelvin. The most common specific heat capacity value that you will come across in questions is that of water. It is 4,200 joules per kilogram per Kelvin. This value means that if we have 1 kilogram of water and we want to raise its temperature by 1 Kelvin or 1 degree Celsius, we have to supply 4,200 joules of energy to the water. Let's see a specific heat capacity example. Here we have to find the specific heat capacity of copper based on an experiment. We know that m, the mass, is equal to 0.35 kilograms, delta T, the change in temperature, is 7 Kelvin, and that the energy supplied is equal to 0.93 kilojoules, which I will convert into joules and get 930 joules. Rearranging our formula for C, we get C is equal to Q over m times delta T. Substituting gives us 930 divided by 0.35 times 7. So C is approximately 380 joules per kilogram per Kelvin. Let's move on to specific latent heat. Specific latent heat is used when a substance undergoes phase change. More specifically, when a substance changes between the solid and the liquid phase, or the liquid and the gas phase. Therefore, we talk about the specific latent heat of fusion and the specific latent heat of vaporization. Both represent the energy required per 1 kilogram of substance to change its phase. Here is the formula for both, along with the variables. From this, it logically follows that the unit of specific latent heat is joules per kilogram. Let's discuss an example. Here we have to find the energy supplied to an ice block while it melts. The mass is 1.3 kilograms. The specific latent heat of fusion of ice is 334 kilojoules per kilogram, which I will write in joules as 334 times 10 to the power of 3 joules per kilogram. Substituting into the formula, we get Q is equal to 1.3 times 334 times 10 to the power of 3. This gives us approximately 434,000 joules for Q, which we can write as 434 kilojoules. So this is the total energy supplied to the ice block. Next, let's see how to work with specific heat capacity and specific latent heat through a more complex example. Here, 4 ice cubes melt in a glass of water, and we have to calculate the final temperature of the water in the glass. Let's divide the situation into two parts. First, we will look at what happens as the ice melts, and then we'll consider the changes that take place while the melted ice water and the water originally in the glass reach the same temperature. Of course, this temperature will be the final temperature of the water in the glass. Let's look at melting. While the ice is melting, its temperature does not change. In terms of energy transfer, the ice gains energy, while the water in the glass loses energy. Since no energy is lost to the environment, these two energy values are equal. So I will write that Qi, the energy supplied to the ice, is equal to Qw, the energy lost by the water. Since the ice is melting, I will use the specific latent heat formula for the energy gained by the ice. So we get Mi, the mass of the ice, times Li, the specific latent heat of fusion of ice. During this process, the water in the glass does not change phase, it just cools down. So here I will use the formula that includes specific heat capacity. This gives us Mw times Cw times delta Tw. The mass of one ice cube is 32 grams, which is 0.032 kilogram. And since there are 4 ice cubes, for the mass of the ice we get 0.032 multiplied by 4 times the specific latent heat of fusion of ice, which is 334 kilojoules per kilogram, and which I will write in joules per kilogram, giving us 334 times 10 to the power of 3. This is equal to the mass of the water, so 0.245 kilograms, times the specific heat capacity of water, so 4200, and we don't know the temperature change of the water. Rearranging for delta Tw and carrying out the calculations, we get approximately 41.5 degrees Celsius for the change in the temperature of the water. This means that the temperature of the water that was originally in the glass, right after the ice has melted, is 72 degrees Celsius minus 41.5 degrees Celsius, and this gives us approximately 30.5 degrees Celsius. Once the ice has melted, the water from the melted ice cubes is still at 0 degrees Celsius. During the second part of the process, the temperature of this water from the ice cubes will increase, and the temperature of the water that was originally in the glass will keep decreasing. When the water from the ice and the water originally in the glass reach the same temperature, energy transfer between them stops. This common temperature is the final temperature of the water in the glass. Let's see how to calculate this temperature. The water from the ice gains energy, and the water originally in the glass loses energy. Again, these two energy values are equal, so I can write that Qi is equal to Qw. Since what was originally ice is now water, there will be no phase change during this process, so we'll use the specific heat capacity equation on both sides. On the left-hand side, this gives us the mass of the ice water, and since on both sides of the equation now we have water, the specific heat capacity will be the same. This is the specific heat capacity of water, and I will simply name it C. This is multiplied by the change in temperature of the ice water. This is equal to the mass of the water originally in the glass, so Mw, times the specific heat capacity, multiplied by the change in the temperature of the water. To make things simpler, I will cancel C from both sides. The mass of the ice, as we've seen before, is 0.032 times 4, and this is multiplied by the ice water's temperature change. We know that the temperature of this ice water will end up at the final temperature, which I will name Tf. We also know that right after melting, the initial temperature of this ice water is 0 degrees. So the change in temperature of the ice water is the final temperature, so Tf, minus the initial temperature, which is 0 degrees. This is equal to the mass of the water, so 0.245, multiplied by the temperature change of this water. The water begins at 30.5 degrees Celsius, and it cools down to its final temperature. The difference between these two is the change in temperature, so we get 30.5 minus Tf. Since we want to keep this temperature change as a positive value, and we know that the final temperature will be lower than 30.5 degrees, Here I wrote 30.5 minus TF instead of writing TF minus 30.5. Working further and simplifying, we get 0.128 times TF equal to 7.4725 minus 0.245 times TF. Rearranging gives us 0.373 TF equals to 7.4725, and dividing we get approximately 20 degrees Celsius for the final temperature of the water. Let's summarize what we have learned in this video. We began by defining specific heat capacity and looking at a formula including specific heat capacity along with the variables. We added that the unit of specific heat capacity is joules per kilogram per Kelvin, and that a common specific heat capacity value that you will often come across in questions is the specific heat capacity of water, which is 4200 joules per kilogram per Kelvin. Next, we moved on to specific latent heat and defined specific latent heat of fusion and specific latent heat of vaporization. Then we saw the formula for specific latent heat along with the variables, and we concluded that the unit of specific latent heat is joules per kilogram. This completes our discussion about specific heat capacity and specific latent heat. In the next video, we'll learn about phase change.